Good morning, everyone. Welcome to the class of CE331, Environmental Engineering 1. So, we were discussing um, iron and manganese and their occurrence in water, especially in Bangladesh, in groundwater. You'll find a lot of iron and manganese in a multitude of areas. So, this is a uh, common problem all over Bangladesh, we can say, in groundwater. Okay, in groundwater. Now, the kinetics of iron oxidation, precipitation, and removal. So, what we were discussing is that um, how to remove iron. That's the thing, right? What you can do is um, this is iron. Iron remains in water in ferrous form. This is aqueous. Okay, how you can remove it? If you oxidize it, if you oxidize it, this iron, then it becomes ferric, and this is actually solid form. So, okay, the compound that it forms, like ferric oxide, then ferric hydroxide. Okay, so these are basically solid, and they precipitate. When you oxidize ferrous to ferric, then you get these types of forms, and they are actually solid, so they precipitate, and therefore they are removed. Therefore they are removed. Okay, so your objective is to oxidize iron to remove. Now, this oxidation can be performed in a multitude of ways. One is aeration. We already discussed what is aeration. So, by mixing air, and air has oxygen in it, and therefore oxygen will mix with iron, ferrous, and it will oxidize it. And you can use chemicals, strong oxidizing agents like potassium permanganate, okay, and potassium dichromate or potassium chromate. So now you need chemicals here. So this is expensive, but here in this process, this is aeration. Air is basically free, so this is preferable. Now, to remove iron by oxidation using aeration, there are certain conditions that to be need to be maintained. Number one is your pH value has to be greater than 7.3. Your pH value has to be greater than 10.5 or 7.3. I mean, basically, the reaction, the aeration, oxidation with aeration is very slow if your pH is 6.5, and very rapid and greater than 7.5. Okay, so we can call it, okay, at least 7.3. You should be, you should have pH value at least 7.3. So pH value must be greater than 7.3 to remove it by aeration. And number B is your alkalinity in water has to be much greater than 130 milligram per liter. So your alkalinity B, your alkalinity has to be much greater than 130 milligram per liter. Okay, and absence of organic matter. If organic matter is present, then your oxidation process uh, will be hindered and it will be slowed down. Okay, so these are the three criteria you have to maintain. And C is absence of, I call it here, absence of organic matter. Is it clear?
Yes, sir.
Yes.
If you want to do it with aeration, or if you use chemical oxidation, then you do not need to meet this criteria because now you have a strong oxidizing agent, chemicals. So if you use chemical oxidation, then you do not need to maintain this criteria. But we prefer this aeration because it doesn't need any chemicals, therefore it is cheaper, inexpensive. Okay, so and usually groundwater has high alkalinity, because of the presence of carbonate and calcium carbonate and other minerals. So criteria and theory of iron removal. First of all, what happens that oxidation of soluble means this is aqueous, soluble ferrous to insoluble ferric plus 3 precipitates through how? Simple aeration only for stripping out carbon dioxide and increase pH value. If you strip out carbon dioxide from water, if you strip out carbon dioxide from water, by the way, carbon dioxide plus water, this is H2CO3, right? That means if you add carbon dioxide, then your pH will, there will be acid, so pH will decrease, right? Now, if you strip out carbon dioxide by aeration, if you aerate this water, then oxygen will go there, and what the carbon dioxide was inside, already inside the water or dissolved, they will go out. Now, if the carbon dioxide goes out, then your pH will increase. So that's your objective here, to increase your pH value. So you aerate your water to increase your pH value to 7.3 at least. Okay, clear? So
Yes.
condition, first of is there are two conditions. Condition one, so we call it condition A, when your alkalinity is high and absence of organic matter. Look, the condition one, this is condition A. Here, alkalinity value is higher. So you just need only simple aeration to increase the pH value 7.3, and then your oxidation will happen. But in condition B, for example, you have another water sample now which has alkalinity value is now less than 130 milligram per liter. In that case, only aeration will not help. So you have to use aeration as well as you have to add alkalinity by alkaline substances, because your alkalinity is now less than 130 milligram per liter. So in that case you can use lime like calcium hydroxide, or you can use caustic soda like sodium hydroxide. Okay, clear?
Yes, sir.
Yes, sir.
Or you can use aeration and then addition of oxidizing substances like chlorine, potash. Like here, using chemicals, they are referring to chemicals like this. We don't use this usually. We use chlorine, okay, as oxidant sometimes, or potash. So multiple tray, or you can use multiple tray catalytic contact oxidation. What's that? I already discussed it uh, in the previous lecture. So what happens here? Look very carefully. This iron, your oxidation is you're performing oxidation and getting in ferric form, which is solid, which is precipitate, and this is basically ferric hydroxide or ferric oxide, and this was aqueous, and they precipitate, right? They precipitate. This is actually solid form. Now, for example, you have a filter, and these are gravel particles, and you're passing water. For example, this is the water. You're passing water, and this is the filter media, and the water is filtering. You're filtering the water. Then the water is getting out from here. Now, what's happening here? So this water here, what is incoming inflow of water that has iron in ferrous form. Now you are spreading the water using a sprinkler, maybe sprinkler, okay, and then they are getting in contact with air, and therefore oxidation is happening, and you are getting ferric. So as the water percolates through this ferrous ion is converted into ferric ion, and that means what you're getting ferric hydroxide, Fe2O3, ferric oxide. So these are basically solid. Remember, these are basically solid. So they will make a layer of solid here. This red color are actually the layer of what? Ferric hydroxide, ferric oxide, these things. Okay. And now there is an advantage of this. One thing is this ferric hydroxide and ferric oxide act as a catalyst and positive catalyst to increase the rate of this reaction. That means if they are present, then this reaction will be faster and easier. That means more and more ferrous will be converted into ferric. That means your removal process will be faster. So in other words, these ferric forms will expedite the reaction rate. So this is interesting that from one side you are getting these compounds, and whatever you are getting, that is eventually helping you to get more and more ferric form. What happens that this is the layer of ferric hydroxide and ferric oxide, right? Now you can see that more ferrous is coming. So these ferrous are adsorbed into the surface of this ferric form. So ferrous is adsorbed into the surface of ferric form, and when they are absorbed, so their oxidation process is faster. So this is and you can use this is a one layer. You can use multiple layers. You can use multiple layers. So that they are calling it multiple tray catalytic contact oxidation. Catalytic because these are the catalyst. So catalytic contact oxidation. Coarse media coated with metal oxide. Did you see coarse media coated with metal oxide? So they are actually calling it metal oxide, ferric hydroxide. Iron is a metal, so metal hydroxide or metal oxides. Okay, clear.
Yes,
So
sir.
if your alkalinity value is low, then to expedite the reaction rate, you can use this process. Multiple track catalytic contact oxidation, or you can add alkaline substances because your alkalinity value is low, or you can use chemical oxidation. So this is the for condition B. For condition B, you can use this, you can use this, or you can use this. But in condition A, you already had alkalinity value higher, so you do not need addition of alkaline substances or these things. So you just only need to simple aeration. But here in condition B, you have to use aeration as well as this addition of alkaline substances or aeration and chemical oxidation. Clear?
Yes, sir.
So that's the first step. And the second step, separation of precipitated ferric particles through solid transfer process like flocculation, sedimentation, and filtration. What we are doing actually, that whatever you are getting this solid, we are retaining this solid using this filter media. Okay. So you see, direct filtration of high iron content aerated water with high turbidity is not recommended by American Water Association. The problem is that it will clog. That means it will create jam of flow by deposition of sand and solid particles. You will need frequent backwashing. You need the wastage of water. You will have wastage of water, and your maintenance cost will high. So we don't use direct filtration. First we do aeration and then we perform direct filtration. Okay. In case of high iron content, we first do aeration and then direct filtration. because if you do aeration, then a significant amount of iron will be removed. Okay, and then you can perform this direct filtration. Now, what about manganese? Exactly same thing happens for manganese. This manganese aqueous form is this aqueous form. Manganese plus 2 form. When you oxidize this, you will get manganese plus 4 form. This is oxidized form, and this is a form which can be represented manganese oxide, and this is solid and it gets precipitated. Same thing. Okay, and by the way, this was for aeration, right? Let's write it here. Manganese plus 2. This was aqueous, and then you are oxidizing this to get manganese plus 4, and which is actually manganese oxide. And this is a solid, so it will precipitate and you can remove it. Okay, now similarly, like this, you need aeration at higher pH value like 9.0. Here you need higher pH value. In case of iron, you needed 7.3, greater than 7.3, but here you need a pH value at least 9. So this is much difficult. You can see that manganese is much more slowly oxidized through aeration than iron. In fact, the rate is negligible at pH value below 9.0. So you need at least 9.0 to have considerable amount of oxidation. So chemical oxidation of manganese requires a pH level above 8.5, and 1.0 milligram of chlorine can oxidize 1.3 milligram of manganese. So if you perform aeration, you need pH value at least 9. If you do chemical oxidation, then you need pH value at least 8.5. Okay, so here, similar to this, you can perform aeration, and then you can perform chemical oxidation. This oxidation process can be performed either aeration or by adding chemicals. Okay, so the condition here is that your pH has to be greater than 9. Okay, and then your pH value has to be greater than 9 here, but here in chemical oxidation your pH value has to be greater than 8.5. Okay, so similar to iron oxidation, regarding catalytic oxidation like this. In manganese also, these in case of here iron, they were acting as catalyst, right? Right?
Yes, sir.
Yes, sir.
In manganese oxidation, this manganese oxide, this is solid, they act as catalyst for this reaction. Catalyst. And this manganese oxide can also act as a catalyst here also. Okay? They can act as a catalyst, positive catalyst, of course, in this reaction also. Basically, these are gelatinous, that means sticky. These layers are gelatinous or sticky, okay? And they can absorb these ions. And for example, this is the coating of manganese oxide, or you can call it ferric oxide or ferric hydroxide, whatever. So when a ferrous or manganese ion comes here, they are adsorbed here. They are adsorbed. And in when they are adsorbed, then it is easier for them to convert to ferric, and easier for this also to convert to Mn plus 4. And therefore this is oxidation is done, and they convert it to solid and therefore are removed. Okay, so that's why they're calling it catalytic oxidation. So previously precipitated iron and manganese, that means previously precipitated, these are the previously precipitated, they make a coating and serves to catalyze the oxidation of manganese, like Mn plus 2 or even from plus 2 to plus 4. Manganese oxidation through chlorine requires 2 to 4 hours to react completely. If you use chemical oxidation, then you need 2 to 4 hours of contact time at least. So yeah, but now the question is how much time you need in case of using aeration. It depends on the type of the water condition, or what is the pH, what is the alkalinity, and these things. Okay. Okay, so criteria and theory of manganese removal. First of all, oxidation of soluble manganese to insoluble manganese, manganese plus 4 precipitates. কিভাবে? Aeration at higher pH value, or you can use chemical oxidation at pH greater than 8.5, or you can use multiple tray catalytic contact oxidation. You need to understand this. I already told you. Multiple tray catalytic contact oxidation. Catalytic contact oxidation. That means they are in contact with this. They are in contact with the catalyst here of manganese plus 2 into manganese plus 4, or direct absorption. Absorption means adsorption of manganese ions on hydroxide and manganese oxide coated surfaces of coarse media. As I told you, they can be adsorbed. They can be adsorbed into these surfaces of, they can be absorbed into the surfaces of this manganese oxide and ferric oxide, hydroxide, these things. Okay. And second process is once you have converted them to solid form, then you can remove them by flocculation, sedimentation, and filtration. Clear?
Yes, sir.
So catalytic oxidation of metal ions and absorption of precipitate. This is important. Okay, this is important. Similarly, the iron removal. This is important. The catalytic oxidation of, as I told you, that the removal of iron and manganese is generally hastened. That means expedited, faster, and made more efficient, swifter, by letting water trickle down. Trickle means percolate down. Trickle, trickle. Okay, the water is passing like this. So trickle down, or rise upward through gravel or other relatively coarse heavy materials coated with coated with hydrox oxide of ferric or manganese plus 4 precipitates by absorption. Actually, they are referring to ferric oxide Mn plus 4, MnO2, this thing. They are referring to this manganese oxide or ferric hydroxide, these things. Okay? Ferric hydroxide, manganese oxide tend to absorb means absorb ferrous ion and manganese ions. You see here that manganese ion and manganese oxide, this is a coating, they adsorb. Dot means they have absorbed it. Okay, this reaction is fast. Okay, so any questions here from here? Any
No,
questions
sir.
that, huh?
No, sir.
Okay, make sure you understand them well. Here is a figure. You can see that contact oxidation. This is catalytic contact oxidation. Okay, so this layer is the ferric hydroxide or manganese oxide coating and adsorption. They can adsorb these layers actually. This indicator shows that this or this can absorb this. That means dot. This dot this. That means adsorption. Okay, and this after they have absorbed into the coating, then this manganese easily oxidized because they are now adsorbed into the coatings, which is catalyst. Okay, what about arsenic? That's also a big problem in Bangladesh. So in groundwater of Bangladesh, mainly we have the problem, majority of the cases we have problem of iron, we have problem of manganese, and we have problem of arsenic. So this is very important for you guys to know their chemistry and the theory of removal from the water. Okay, do you anyone um, does anyone from you have experience of these types of problems? And back to your uh, hometown where you use groundwater, you may observe these problems. Okay, because these are widespread problems throughout Bangladesh. So we are done with iron removal. We are done with manganese removal. Now we'll deal with arsenic removal. You know what? In nature, arsenic is generally found only in the trivalent and pentavalent form. You know that arsenic has several forms. Among them, we Uh, Usually in nature, we usually found it in trivalent arsenic 3 and pentavalent arsenic 5 states. Arsenic 3 present in a typical water supply would occur as in this form. In typical water supply, it will be usually in this form. So this is an undissociated weak acid is predominant in the pH range of 2 to 9. So here arsenic is in this form, trivalent form. Arsenic 5 in water occur as a strong acid and dissociates into ions according to the pH value. Both arsenate and arsenite adsorb strongly on hydrous oxide surfaces of a wide range of solids including iron, aluminium, and manganese oxides. Therefore, oxidation of ionization of non-ionized arsenic to ionized arsenic through adding oxidizing agents or direct ionization of arsenic 3 through increasing pH 9 is the first step of ionic removal. So what they are referring to here, if you look at the arsenic species under different environmental conditions, you have arsenic 3 and you have arsenic 5. Occurrence. Uh, Arsenic 3 is predominant in reducing conditions. Okay? Lower redox potential occur as undissociated weak acid, arsenous acid like this. Arsenous acid. In case of pentavalent form, this has high redox potential in contrast to trivalent form, where it has lower oxidation redox potential. In pentavalent form, it has high redox potential. Here it was undissociated weak acid. This is not WEK. This is WEAK, weak. Okay, the spelling mistake, weak acid. But here it is a strong acid. Species. What are the species? If pH is greater than 8.0, dissociates into arsenite ion. This is one arsenite ion. If pH is greater than 11, it is in this form, arsenite ion. If pH is less than 7, this is in this form. If pH is 7 to 11.5, this is in this form. If pH is greater than 11.5, it's in this form. Usually in our drinking water, we have pH 7 to 8 range. In drinking water, we have pH 7 to 8 range. Okay? Approximately. Or 6.5 to 8.5, something like that. So this is, you will get mostly in this form. You'll get mostly this form. What they are calling arsenite ion and what they are calling arsenate ion. For trivalent form, they are calling it arsenite, and for pentavalent form, they are calling it arsenate. Again, for trivalent form, they are calling it nite, and for pentavalent form, they are calling it net. Clear?
Yes, sir.
Again, for trivalent form, they are calling it arsenite, and for pentavalent form, they are calling it arsenate. Okay. Uh, If you look at here, H2ASO3 minus H2AS arsenic O3 minus. We can write for hydrogen this is plus 1, right? So hydrogen is plus 1 multiplied by 2. For arsenic, we don't know. That's we need to find it out. Into arsenic, how many arsenic? One arsenic ion. So 1 plus for oxygen it is minus 2 valency. We are looking at the valency. What is the valency of hydrogen? Plus 1. Arsenic we don't know. For oxygen is minus 2. And how many oxygens? 3. So we multiply it to 3 equals to minus 1. So if you solve it out, you'll get 2 plus x minus 6 equals to minus 1. So from here you get x equals to minus 1 plus 4 and you got 3. So that means here the valency of arsenic is plus 3 and that's why you are calling it arsenite. Here similarly in this form if you calculate you will find it plus 3, but here if you calculate you will find plus 5. That's why they are arsenate ion. All are arsenate ion. This is an arsenate ion, this is an arsenate ion, these are all arsenate ions. Okay, now the thing is, look at this uh, look at these uh, forms. They have a negative ion. Did you see? Huh? They have a negative ion. They have a negative ion, negative ion, negative ion. Did you say them?
Yes, sir.
But here you see that there is no negative ions. Arsenate is it. Okay. So how you can remove it? Look, both arsenate and arsenite ions adsorb strongly on hydrous oxide surfaces of a wide range of solids. But when they are non-ionized form, they cannot be adsorbed. So your objective is to your objective is to um, here your objective is to oxidation and ionization of non-ionized arsenite ion to arsenate ion, from this to this, or from this to this. Arsenate ion means pentavalent, arsenite ion trivalent. What I am trying to say here is this, that uh, in nature you will find this or pentavalent form. Now you want to remove it. You have this in your water and you want to remove arsenic. But the problem here is this, since it does not have any ions, any charge exclusively, therefore it cannot be removed easily by adsorption into coating of ferrous hydroxide, ferric hydroxide and others. But when you can convert these to this, for example H2ASO3 minus, if you can convert this H2ASO3 minus, then this ionized form, it has an it has an ion. Did you see? This ionized form can be easily adsorbed in ferric hydroxide coating and removed, but this cannot be done because it doesn't have any charge. So your objective is to convert this ion, sorry, this form to this form. Is it clear? Is it clear?
Yes, sir.
Okay. If you have any questions, then you can tell me. I will repeat. So your objective is to convert this form into this form so that they can have a charge and which can easily be absorbed into these coatings. So that's why the theory here is this, that ox dissociation and ionization of non-ionized arsenic, this is non-ionized, this is non-ionized, to arsenite, negative charged arsenite ion, to negative charge arsenide ion. Okay, or oxidation and ionization of non-ionized arsenite to ionized arsenate form, or from 3 to 5, through adding oxidizing agent like chlorine or potash. And dissociation or ionization of non-ionized arsenic to this form through adding lime or increasing of pH value greater than 9.0. So you can either take this step method or you can take this method, or okay. And then finally, when they are adsorbed, then you can co-precipitate of ionized negative charge arsenic ion with settlable solid phases flux. Okay, what we are calling it, like ferric oxide or ferric hydroxide. Okay, if you have gravel, if you have gravel, then you have coatings of, these are the coatings of ferric hydroxide. Okay, and whenever this charged ion comes, they will be absorbed here and therefore will be removed. Okay, now if we compare the process here, you will see that for iron we can do aeration and you need a pH value greater than 7.5 by oxidation through aeration. In case of manganese removal, we need pH value greater than 9.0 by using aeration, or greater than 8.5 if we use chemical oxidation. In case of arsenic, here is the problem. Aeration will not help. This is not easy. Arsenic removal is not easy. It's expensive. That's the problem. So aeration will not help here. You will need to have chemical oxidants like chlorine or potash. Okay, chlorine or potash to convert this arsenite non-ionized to ionized form of pentavalent. Okay, so Yeah, and this pentavalent form, you can find it either this pH range or this pH range. Or in case of arsenic, you can also use lime, calcium oxide or calcium hydroxide to convert this non-ionized trivalent to ionized trivalent. Ionized means negative charged. And once they have negative charge, they can be adsorbed. Once they have negative charge, they can be adsorbed into the coatings. That's how we remove it. Okay. So this is a good figure which shows the um, similarities and differences among the removal of these three types of elements from water. Okay, clear? Clear, guys?
স্যার আরেকবার একটু বলুন।
I mean, this figure shows which one you want me to repeat.
Yeah.
I mean, this figure shows you the differences among these iron, manganese, and arsenic removal. Similarities and differences.
ও আচ্ছা, বুঝছি।
Yeah. I mean, here you need pH range this, you need pH range this in manganese, in arsenic, you need pH range this, and you need aeration here, aeration or chemical oxidation here, but in arsenic, your aeration is not gonna help. Okay, this is not cheap. So, if you could use aeration, then it would have been cheap, but you cannot use aeration here because it doesn't help. So you use chemical oxidation, or you can use lime to convert this
Okay.
charged ion. This charged ion. You need these charged ions. So because these charged ions only are able to be adsorbed into these coatings. These no, they will not adsorb here. This yes, they will adsorb. So you need to convert them from this to this. And due to this, and if to make this conversion, you need chemicals here. To conversion from there to there, you need chemicals here. Okay.
Yes, sir.
So arsenic is can be possible through this method or this method. Both are for arsenic, A and B. Okay, A and B. Co-precipitation. Sometimes if you have all of them in your water or multiples, like you have iron, you have manganese, you also have arsenic, everything. So in that case, you can co-precipitate in the filter media. They all can co-precipitate. Co means at a time, all together, simultaneously. Okay, so co-precipitation or absorption of arsenic into solid phases. So this ferric oxide, this coating can be of this coating, as I told you, where here these coatings can be of ferric hydroxide, or it can be of manganese oxide, it can be of aluminum hydroxide also. These all act as catalytic or adsorbent, which can adsorb manganese ion, arsenate ion, negative charge of course, arsenite ion, of course negative charged. Okay. So this is also just the steps of this, how you can co-precipitate these things. Okay. So here the thing is, when you have these pollutants in water, you add necessary For example, you have arsenic and iron in water. You add potash, okay, compounds of potassium, so potash, and then you sediment them. Sedimentation, it means, the chamber, for example, your water is coming first, and then it's your sedimentation basin, okay? Sedimentation, we already know sedimentation. So the water will flow in through the sedimentation, the solid particle will flow. You add potash, and then there will be solid particles, they will fall down, and then from there you use a filter. You don't directly give it to the filter, because otherwise it will clog down the filter faster and your maintenance cost will be higher. Okay, and there are other problems. So first we put this in a sedimentation tank and remove the pollutants to some extent, and then we put this here so that the performance of the filter is better. Okay, so you see, before putting it into the filter, in all cases they have sedimented it. Okay, clear? Hello, clear?
Yes, sir.
Yes, sir.
Yes, sir.
Y- you see the difference here. They're adding potash here, but here they're adding potash as well as aluminum or iron salt. Why? Because you did not have iron here. Sorry, you did not have iron here, but you have iron here. Since you have iron here, you will form this. You'll form these coatings by already existing iron in water. But here you do not have iron. Then where you are gonna get these coatings from? Where you are gonna get this coating from? You have to add iron. You have to add iron, because in your water you don't have iron, so you have to add iron along with potash. Clear? You do not have iron here, so you have to add iron to get the coatings. That's what. Clear?
Yes, sir.
That's also possible. If you have arsenic and iron content water, you add lime at pH greater than 9.0 and mix it. Okay. Cloth and sand filtration, and here finally they are using activated alumina filtration or iron coated sand filtration. Yeah, so that's it about the removal of iron, manganese and arsenic. Okay, now desalination, this is also a big problem in Bangladesh, uh, especially in southern area of Bangladesh. If you have the map like this, Bangladesh, you have Bay of Bengal here, right? You have ocean here, and ocean water is salty. Now, if you have rivers in this zone, ocean water can intrude into this coastal water, coastal fresh water. Okay, and remember, ocean water has total dissolved solid salinity at le- at a level of 35,000 milligram per liter, but here maybe what, 500, right? So it's a big huge gap. So this can pollute this ocean water. If they come to the rivers here, they can significantly add salinity into this fresh water. And if you have salinity, then high salinity, then your crop cannot survive. You cannot use this water for irrigation, for agriculture purpose. You cannot drink this water. So that's a huge problem, and this problem is exacerbated by a process of which that if if you see the Jamuna and these rivers, they are flowing from there to there, from north to south, from north to south. Okay, this is south. So therefore, this flow actually hinders this flow. Now, if you put a dam here, like Farakkabad and this dam and these things, then this flow will be lower, upstream flow, and therefore you're giving this ocean flow more chance to come to the inland and pollute more and more water by salinity. Okay, so this problem is aggravated uh, by this phenomena, these man-made and other natural phenomena. So the problem here in southern part of Bangladesh, these people, they are facing this salinity problem a lot. Now the problem is desalination. Desalination means is to D, that means removing the salinity, and desalination means removing the salinity. Desalination process is not easy. This is expensive. This is expensive. Ocean water has dissolved salts content of about 35,000 milligram per liter, as I told you. Many groundwater supplies are brackish. Dissolved salts 1,000 to 3,000 milligram per liter and too salty for consumption. No simple technique is available, and the cost of desalination is still relatively high. Okay, so desalination system can be separated into those which employ phase change like distillation or freezing and this. So another problem I just remember that with climate change effect, your sea level will rise, and if your sea level rises, then you have more and more water, ocean water, intruding into the inland, and more salinity pollution. Okay, that's another reason. So anyway, so as we were discussing that there is no simple technique available for desalination. We can use different techniques. For example, evaporation. We can evaporate the water and leaving that's the solid salt behind. Then you can use solar stills, you can use freezing, we can use ion exchange. So these are basically physical separation, and this is kind of related with electricity and chemicals. So ion exchange has been applied by desalting by using hydrogen and hydroxyl based resins. Okay, this like a filter. Electrodialysis, that's another process. You use electricity, anode and cathode, and you use a membrane here. Okay, you use a membrane here where only sodium can pass, nothing else can pass. Okay, so employs electrical energy to drive dissolved ionized solids across semi-permeable membrane. What is semi-permeable? Semi-permeable means um, it can it permits some agents to pass through, but it hinders or stops other agents to pass. That's semi-permeable membrane. That means, for example, this is a membrane here. Okay, this is a membrane. Now, what is happening from there? A can pass, but B cannot pass. This is semi-permeable. Why? Because maybe A is smaller in size, B is larger in size, so it cannot pass through the pores of this media. Okay, so this is called semi-permeable membrane. Okay, semi The system consists of cathodic and anionic semi-permeable membrane and two electrodes. This is, you see, this is cation membrane and this is anion membrane. That means this membrane allows to pass only the cations, and this is anion membrane. This membrane only allows anions, negative charge, to pass through. In contrast, this cation membrane only allows positive charge, that means cations, to pass through. Okay, now if you use negative charge here and positive charge here, and salt is basically what? Sodium chloride, right? Calcium ions and these things. So if you apply electric charge, then this negative charge will attract the positive charge, which will pass through there, and this positive charge will attract the negative charge. And if you have H2O here, then your sodium ion and chlorine will be removed from there and there, and you'll get fresh water. That means you are removing chlorine, you're removing salt of water from water. Okay. Electrodialysis process. There is another process, that is reverse osmosis. Reverse osmosis. So this is the name itself tells you that this is something that is a reverse to osmosis. First, let's see what is osmosis. If you have salt water here, so I mean saline water, let's call it saline water. This is adjective, saline water, and this is fresh water. Fresh water, and this is saline water. So this is saline, salt is there. Okay. Now if you put a membrane here, then what would happen? If you put a membrane, semi-permeable membrane here, then what would happen? Water molecule will pass from there to there. Am I right? Fresh water will
Yes.
pass from there to there because you have less freshwater concentration here. So freshwater will flow from there to there. Okay. Now this is semi-permeable membrane. This is semi-permeable membrane. Okay. Fine. So water will pass through there. Now, why water will pass through there, by the way? Because water has low concentration here, high concentration here. Water concentration is higher here, lower here. So water will pass from higher to lower concentration. So this is osmosis basically. Okay. Now you have a force. That means you have a force from there to there. You have a pressure. So this is natural. Now what happens if we create a pressure from outside? If we create a pressure, if you create a pressure here, then what happens? Your flow of water from there to there will be slowed down, and for example, this is F prime. Okay. Now when F equals to F prime, then this flow will be stopped, right? Let's call F is osmotic pressure. When your applied force F prime, or pressure, let's call it pressure, is equal to the osmotic pressure, P is equal to P prime, then it will be stopped, right? Now what happens if your P prime is greater than P? Then what would happen? Water will flow from there to there. Remember, this is a semi-permeable membrane. That means water can pass through, but salt cannot pass through. Water can pass through, but salt cannot pass through. The semi-permeable membrane has four openings which are larger than the molecular size of water but smaller than those of the salts. That means from this semi-permeable membrane, water can pass, but salt cannot pass. Okay, so if you're applying pressure, then what would happen? Salt cannot pass through, so water will pass through. So you see, in osmotic natural osmosis, what was happening? Water was flowing from there to there. Now you're applying pressure to reverse the direction to there. So this is reverse osmosis. This is reverse osmosis. Okay, so you have to apply pressure and you are driving out water from saline water. You're driving out water from saline water. So you are making it clean. Okay, clear?
Yes, sir.
So this is the pressure, and you need if a grade you need 20 to 30. No, you need 1500 psi pressure is usually 5 to 50 times higher than the osmotic pressure, as high as 1500 psi. So you need to apply a pressure 5 to 50 times the osmotic pressure. That if this is the osmotic pressure, P prime has to be 5 to 50 times of P. 5 to 50 times of P for reverse osmosis. Okay, this was osmosis and this is reverse osmosis. This direction was osmosis, and this direction, the opposite from right to left, this is reverse osmosis. Okay, so this is the just the explanation whatever I have told you so far. So that's all for today. You have any questions, guys?
No, sir.
Sir,
Yes, go ahead. Okay, so thank you very much, guys, for attending the class. Have a good one and stay safe.